Chapter 3 Matter, Energy, and the Universe. Section 3.2 Matter. At the birth of the universe, two things were created: matter and energy. I'm now going to describe what matter is. Matter makes up some of the substances that are found within the universe. There's also dark matter and dark energy. However, physicists aren't quite sure what these things are. So as I said, it seems that substances in the universe can be composed of matter. All matter is made up of elements. Chemists have discovered 115 different elements. You're familiar with some of them from high school: hydrogen, helium, gold, carbon. Each one of these elements has unique properties. Each one of these elements is distinct chemically. If you want to know more about elements, take a look at the website www.webelements.com. So this image shows the periodic table, and chemists have organized the different elements based on their characteristics. Some elements are metallic, some are non-metallic. Some elements are in gas form in their natural state. Some elements are in solid form. If we were to take a look at matter, the smallest bit of matter that you can have that has unique chemical characteristics, that it's still helium or hydrogen or gold, is an atom. Atoms are composed of even smaller particles called protons, neutrons, and electrons. When chemists refer to an atom's atomic number, or an element's, atomic number, what we're talking about is the total number of protons. The number of protons found in the nuclei of different elements is unique. For example, hydrogen has only one proton in its nucleus. Helium has 2, oxygen has 8, and carbon has 6. Atomic mass number is an atom's total number of neutrons and protons. Many elements have unequal numbers of neutrons and protons. For example, sodium has 11 protons and 12 neutrons, so its atomic mass number is 23. Here we see a representation of carbon-12. This is natural form of carbon. It also exists in variants called isotopes. Carbon-12 in its nucleus has 6 neutrons and 6 protons. Circling the nucleus are the electrons, and they occur in 2 orbital shells. The first shell has 2 electrons. The second shell has 4 electrons. Atomic weight is another important definition. It refers to the total weight of neutrons, protons, and electrons. Now, as I said, some elements can have variants, different numbers of neutrons, but similar numbers of protons. We call these variants isotopes. So, for example, carbon-12 is the most common form of carbon, but there is a form of carbon called carbon-14. Carbon-14 has 8 neutrons and 6 protons. Some isotopes are unstable. They lose subatomic particles, and this causes them to change from one element to another element with a lower atomic mass. So, for example, uranium, if it's an unstable element, if enough particles are lost, it will turn into lead. This process of losing subatomic particles is called radioactive decay. And we use radioactive decay to date objects when they formed in Earth history. Let's go back to some of these subatomic particles found within an atom. So protons have a positive electrical charge. Electrons are negatively charged. The net charge, whether it's positive or negative, is determined by the ratio of protons and electrons. Neutral charge occurs when the number of protons is equivalent to the number of electrons. If there's more electrons than protons, then you're going to have a negatively charged atom. If there's more protons than electrons, then you're going to have a positively charged atom. Elements with a net positive or negative charge are called ions. Positive and negative ions are electrically attracted to each other. This mutual attraction allows for bonding of atoms, forming more complex structure than a single atom of one element. It can form molecules and compounds. A molecule is similar atoms bonded together. Atoms of different elements joined together form compounds. So in the top row of this diagram, we see 4 different molecules where similar atoms of the same element are bonded together. So hydrogen, oxygen, nitrogen, and chlorine. In the bottom row, we see compounds. First one is nitrogen oxide, the bonding of nitrogen and oxygen. The second one is water, the bonding of 2 hydrogen to an oxygen. The third compound is nitrogen dioxide, so 2 oxygen atoms bonded to 1 nitrogen element. And then finally, carbon dioxide, 2 oxygen bonded to a carbon atom. Here we see the molecular structure of table salt. So this would be a compound. 2 different elements are joined together, chlorine and sodium, and this forms salt. On its own, chlorine is a toxic element. Now, matter has some interesting properties. And let's describe 3 of these properties, these physical properties. The first one is called mass. Mass refers to the amount of matter found in an object as measured in grams or kilograms. It is important to note that mass is not the same thing as weight. Weight depends on gravity. So we could have identical masses, one on the Earth, one on the Moon. Because gravity is greater on the Earth, that mass on the Earth would weigh more. Another important physical property of matter is volume. And volume is the measure of the amount of space occupied by an object composed of material. It's measured either in centimeters cubed or meters cubed. Density is the quantity of mass found in a given volume. So if we had the same volume of hydrogen and lead, lead would be much more dense. Phases of matter. Matter can exist in 3 common phases: solid, liquid, and gas. What's really important to take note about these phases is that the change from one phase to another is influenced by kinetic energy, the kinetic energy that exists at the atomic level. When a substance goes from solid to liquid to gas, it has to gain kinetic energy in order for the molecules and atoms to move much faster, allowing for them to change phase. When matter goes from gas to liquid to solid, it has to lose kinetic energy from the atomic level. So, for example, steaming water, gaseous water, has a lot more energy in its atoms, causing them to move quickly. If we remove that energy and cause those atoms to cool, there is a net loss of kinetic energy to the environment. Compounds and molecules made in living tissues are referred to as being organic. Forms of matter not formed by living things are termed inorganic. If you look at organic compounds and molecules, you'll see that there are 4 different categories of substances: lipids, carbohydrates, proteins, and nucleic acids. Lipids are organic matter composed of carbon atoms that have 2 hydrogen atoms attached. Lipids are commonly known as fats and oils. They also belong to the family of molecules known as hydrocarbons. Carbohydrates are organic compounds composed of carbon, oxygen, and hydrogen. So notice the difference between lipids is the addition of oxygen. Some examples of carbohydrates include sugars, starch, and cellulose. Proteins are very complex organic molecules created by living things. These proteins contain carbon, hydrogen, nitrogen, and some other minor elements that are arranged into 20 different compounds known as amino acids. Nucleic acids are very complex organic molecules composed of primarily of different combinations of carbon, hydrogen, nitrogen, oxygen, and phosphorus. DNA, the genetic blueprint of life, is an example of a nucleic acid. Basic building blocks of life, cells. So if you looked at organisms that are found, living organisms that are found on the earth, you'll see that they're composed of minimally one cell or many cells. There are many organisms that exist as just one individual self-functioning unit. Cells are where processes of metabolism and heredity occur. Some general groups of single-celled organisms include bacteria, archaea, cyanobacteria. These cells are very, very simple in structure and function. These cells are also known as prokaryotes. Cells of plants and animals are more complex. We call these types of cells eukaryotes. So here we have an example of a prokaryote cell, and some of the dominant features. As you can see, I've illustrated 6 of these features. Now let's compare this to a more complex eukaryote cell, like a plant cell. So we can see many more features associated with a plant cell, and many of the things that are described here, like mitochondria, endoplasmic reticulum, Golgi complex, we call these organelles. Here we see an animal cell. Once again, many complex features inside it that help it function, to metabolize. And it's far more complex than the simple prokaryotes. Cells and organisms can be classified according to how they obtain their energy. Some cells have the ability to use and process light or chemical energy found in their outside environment to run their metabolism. We call these types of cells autotrophs. The most obvious example of an autotroph are photosynthetic plants. Plant autotrophs create chemical energy from sunlight inside organelles called chloroplasts. In this image, the green circular globs are chloroplasts, and they're creating organic energy from light energy. Some single-celled or multi-celled organisms can create their energy by consuming other organisms. Such organisms are called heterotrophs. Heterotrophs include most types of bacteria and all of the animal and fungi species. Here we see a single-celled heterotrophic organism known as the amoeba. As already mentioned, some forms of life consist of a single cell. Examples include bacteria, algae, and protozoa as general groups. Most organisms are multicellular. In multicellular organisms, groups of cells can have a special function. They can become tissues. An organ is a structure composed of several different tissue types that work together for some purpose. Like our heart, it contains muscle tissues, blood vessel tissues, nervous tissue, and it works to pump blood throughout our body. Multicellular organisms can often have several different types of organs, and each one of these organs has a specific structure and a particular function to help that organism live.